All right. So we are going to talk about the comparison test. This is what I gave just a brief intro last time. The comparison test. This is another test for convergence of series, the comparison test. And I will just remind you of what it says. So this is only for use when all terms are positive. And this is a major restriction, but like all of the various convergence tests we talk about have some kind of limitations because, as I said last time, there are no known series convergence tests which always work. So this is for use when all terms are positive. And sorry, I had a little announcement. Can I just put an announcement in the box here? This happens every so often during the semester. We have visiting people come and give talks in the math department about mathematical things. So I don't know if anybody is interested, but the on Monday at 4 p.m. and this is going to be in the library, like the big room downstairs. I don't know what number that room is, but if you go down the stairs, there's like a big sort of auditorium type room, library downstairs. The colloquium talk next week will be given by my dear friend, visiting PhD student Alejandro Majadas Mure from Spain. He's the one I went to Spain towards the beginning of the semester to visit him, and now he's here visiting me, and he's going to give a talk about. I actually don't remember the title. He probably had a fancier title, but it's about homotopy groups of spheres. I don't expect you to know what any of that means, except spheres and perhaps of. But these are, he's going to talk about some very geometric type things. There will be lots of pictures, and he will mention some currently unsolved problems in mathematics. So if you're into that kind of thing, come on down, check it out. I hope he does a good job too. Any questions about that? Check it out. Okay, anyway, let's talk about the comparison test. This is used when all terms are positive, but the idea is you compare a bigger series to a smaller one. So if, let's say, an is always greater or equal to bn, then there were two parts. So I'm thinking of the a's as being bigger than the b's. And the idea here is if the sum of the a's converges, then the sum of the b's converges. The idea is if you have a bigger one and a smaller one, and the bigger one converges, like the bigger one is not infinity, then the smaller one also cannot be infinity. This is the idea. It's a very simple idea, in my opinion. This is the idea of the convergence test. If the bigger one converges, automatically it means the smaller one converges. And actually, in that case, you can say, this is another sort of obvious fact, whatever the bigger one converges to, that answer must be bigger than whatever the smaller one converges to. All right? So if the big one converges, then the smaller one also converges. And you can also say, and you have to make sure you get this the right way around, if the smaller one diverges, that means like if there's a bigger and a smaller, and the smaller goes to infinity, then automatically the bigger also goes to infinity. So if the smaller one diverges, then the bigger one diverges. All right? This is called the comparison test. And the way in which you use this is you use it to compare a given series to one which you already know. And the ones which you already know, I will just refresh our memory. The ones which we already know are the geometric series and the p series. So if it's geometric, that one looks like ar to the n minus 1. Or sometimes they just look like ar to the n or just r to the n. These are geometric. And this converges, I hope everybody remembers, when absolute value r is less than 1. And it diverges otherwise. That is absolute value r greater or equal to 1, right? That's the geometric series. And these we talked about last week, and you worked with these on the homework and I suppose on the quiz. And there's also the p series, which we just talked about last time. This is the p series. And this one converges when p greater than 1, and it diverges when p less than or equal to 1. All right? So the idea is you just remember these ones. These are like the standard examples, and you just have to remember these. And if I give you another weird one, you try to compare it with one of these that you are already familiar with. That's the idea behind the comparison test. You, on the homework or when you're doing this, you are presented with some weird series. It doesn't exactly look like those, but you can compare it to one of these. And these you already know how to understand properly. All right, so I got a few examples, and then I got some for you all to try. How about this here? 2 over n cubed plus 3n plus 7. And the question is, does it converge or not? Typically, these are going to be too hard to actually say what it converges to, but we can ask, does it converge or not? All right? Now, these can be a little tricky because you need to have some kind of, I suppose, minimal amount of creativity. You have to look at that and ask yourself, what does this look like in terms of the series which I am already familiar with? What does it look like? Anybody have any thoughts? Does it look more like a p series or more like a geometric? It doesn't, it's not exactly either of those, but you got an idea? No, you got an idea?
P series is like 1 over n in the third.
Yeah, I would say this looks more like a p series because p series is one in which you have n to some power, which I do kind of see down here. I see n to some power with some other stuff. It does not look like a geometric to me. Geometric has n inside the exponent, all right? So when I see that, I'm thinking p series with this. And you'll see as we do examples of these, I'm actually thinking that that looks a lot like n cubed on the bottom. N cubed is kind of like the most significant term between those three things on the bottom. So when I see this, I'm going to compare with 1 over n cubed, all right? And this is kind of this is what I said. You have to have some amount of creativity. Like you just have to come up with that out of nowhere. It's not really out of nowhere, but you have to know how to look at the example that you're given and decide for yourself, what does that kind of look like? And now I need to write some kind of comparison like so. In the middle, I'm going to put an inequality. Is this lesser or greater or what? Actually, I don't really like 1 over n cubed. Would you mind? It doesn't matter. I'm going to compare with 2 over n cubed. Just because that 2 is just going to multiply everything by a constant. The 2 up top is really fairly irrelevant. What do you say about those two fractions? I would like to put a less than or a greater than there. Anybody have an idea? Yeah?
It would be greater than, or well, 2 over n to 3 would be greater than.
The one on the right is bigger, you
Yes.
say. Yes. Why is that?
Because n cubed plus 3n plus 7 is always going to be a bigger denominator, which is 2.
Yeah, right. The one on the right is bigger because the one on the left has a bigger denominator. This also, in my opinion, is kind of confusing. You have to, at least when I think about these, I have to think very carefully and make sure I'm not writing it the wrong way around. But that's true, and the reason is because the denominator on the left is bigger, right? Those are two fractions which are otherwise equal, but the denominator on the left side is bigger. And that's why the one on the left The number is a smaller number, all right? Okay, so I have my smaller and my bigger, and we know the bigger, that is to say the series 2 over n cubed, this converges because it's a p series, p equals 3. And I hope everybody has this basic fact memorized, which you can see at the top there. When it's a p series, it converges when p is greater than 1. And this is an example where p is 3. So that one does converge. So the bigger converges. By the comparison test, that means the smaller also converges. So the smaller converges. All right? And that's what we were trying to demonstrate all this time. So 2 over n cubed plus 3n plus 7 converges. That's my answer. All right? So there's a lot of, these in my opinion are a little tricky. You have to come up with this first, just decide on your own what you want to compare it with, and then make sure you get the various inequalities going the right way around. All right. I got a couple more, and then I got some for yous. How about, come on now. How about the sum sine squared of n over 2 to the n? How you like that? This is fairly weird, but we can use the comparison test. So again, I want to look at that and decide for myself, does this look like a geometric series or like a p series? And remember what those are. The p series is the one where you have n to some power. The geometric is where you have n as the exponent. Any thoughts about this one here? Looks more like a geometric to me because I see an n inside of the exponent. And so I will say this looks geometric. I'm going to compare with the appropriate geometric in this example would just be like 1 over 2 to the n, all right? Or if you like writing things all in the power of n, it would be that. Those are the same thing, all right? 1/2 to the n. And so now think about which way shall our inequality go. So I'm comparing sine squared of n over 2 to the n versus 1 over 2 to the n. Which one is which way should the alligator mouth go? Did you all learn about the alligator mouth? This is how I learned inequalities. I was always confused by this as a kid. You want to hear what my confusing teacher said to me when I was a kid? Like if you write, say, 3 less than 5, right? How do you remember what that means? Well, this is like the alligator mouth right here. There's the alligator. And the alligator likes to eat the bigger one. So that's how you know that the 5 is the bigger one and the 3 is the smaller one. How you like that? This is how I learned it. But then, to me, that's not very confusing. But then my teacher also said, and if you don't like that, here's another way. This is like the mouse. I put the ear in front, right? The mouse likes to eat the smaller one, huh? Yeah. For some reason, I still remember this, and I still remember that this confused me because after learning this, I was like, oh yeah, okay. But then I always wondered to myself, like, how do I know if it's the alligator or the mouse? The answer is like, it's both. It doesn't matter. But for some reason, it made me more confused. Are you more confused now that I said all that? What do you think? Right here? Any thoughts? Is it less than or greater than? Which one's greater?
The sign.
The sign is greater? Any other thoughts? The bottoms are equal, right? So really the question is just like, what about the numerators? Is sine squared of n bigger or less than 1? Sine squared of n, of course, is the same as sine of n squared, right? I think the sine of n is always less than 1. It's between minus 1 and 1, right? And when you square it, it's still going to be between minus 1 and 1. So this goes that way. This is because sine squared of n is always less than 1. Because the sine of anything is always, in absolute value, the sine of anything is less than 1. And then if I square it, it's still going to be less than 1. All right? All right, slightly tricky. But anyway, let's continue then. So I'm comparing with this. And now what about that one? This is the bigger one. Does it converge or not? So the bigger is the sum 1 over 2 to the n, which you can also write as sum 1/2 to the n, right? That's geometric where the r is a half, right? The r is always like, just like, if you can write the series as something to the n power, the r is just the number which is inside of the nth power here. So this is geometric r equals a half. And so, does that converge or not? It does converge. Remember, the rule is absolute value r less than 1 means it converges. So this one converges. And so the bigger converges. So that means the smaller also converges. And that's what we started with. Sine squared n over n converges. All right. This is how we do it. All right. I thought maybe it'd be helpful to give some sort of pro tips when you're doing with these inequalities, because I think these are a little tricky to work with. So I will say some pro tips, some life hacks, if you will, for inequalities. We are often going to be dealing with inequalities which involve fractions, and so we can, here's my 2 pro tips. We can, let me just say it like this, discard added, well, can I say, we can discard terms in the numerator, positive terms in the numerator, using greater. For example, if I had something like e to the n plus 5 over n squared, that's greater than e to the n over n squared, right? The whole point is to start with a weird thing and make it simpler using your inequality. And this is one way in which you can do that. If you have things added together, you can just throw away some of those added parts using a greater than sign. If it's in the numerator, you use a greater than sign. If that's in the denominator, it goes the other way around. So we can discard, I'm going to say the other way around, we can discard positive terms in the denominator using the other way. So this would look like, I'll just write the same thing but upside down. N squared over e to the n plus 5. This is less than n squared over e to the n. All right. So if you're throwing things away in the denominator, it gets bigger. If you're throwing things away in the numerator, it gets smaller. And this can be tricky to keep straight, but it's just because smaller numerator makes the whole fraction smaller, and a bigger denominator makes the whole fraction smaller. All right. These are my life hacks. And you have to be sure that your inequalities go the right way. So this is a little cautionary tale here. Make sure it goes the right way. For example, if I started with something like 1 over n squared plus 4, I can use my inequality to turn this into 1 over n squared, and it would be that way, right? Because I just took something out of the denominator, which makes the whole fraction bigger. All right? So that is less than that, and this converges because it's a p-series. With p equals 2, right? Remember the rule for p-series is if the p is greater than 1, it converges. And so that means that's the bigger, and so then the other one also converges. Right? That actually, this is a proper use of the comparison test. I said make sure it goes the right way. Here's an improper, here's a bogus one, and you will see it's actually easy to get this confused and do it the wrong way around. For example, if I have 1 over n plus 4, I'm going to write just like the same thing, but with an n instead of n squareds. So 1 over n plus 4, again, this is less than, for the same reasons, just 1 over n. And here I have 1 over n. That's the harmonic series, which we know diverges. This one diverges. So then the sum 1 over n plus 4 diverges. There's actually something wrong with this. This is not correct, what I wrote here. Anybody see the problem? It's pretty similar to the one I wrote up there. Although I said make sure it goes the right way. Here I said something the wrong way around. Yeah?
With 1 over n being greater than 1 over n plus 4, you can't prove divergence of the smaller one.
Yeah, right. It's because here, this is the bigger one, and I said the bigger one diverges. It's like the bigger one is infinity. That doesn't mean the smaller one is also infinity, right? If the smaller one is infinity, then the bigger one also has to be infinity. But the other way around is not valid. Now it's actually a fact. This one really does diverge, but it's not for these reasons. You have to do a little bit more work to actually show that. So here I did it the wrong way around. This the problem here was we had the bigger diverges, but this doesn't mean that won't imply that the smaller diverges, right? The comparison test says if the bigger one converges, then the smaller one converges, and if the smaller diverges, then the bigger diverges. But this is the wrong way around, all right? So you just can't argue it in that way. Yes?
Couldn't you just use the integral test also? And prove that
Yeah. This is a good candidate for the integral test. Yeah. 1 over n, the improper integral gives you just one ln of n. The other one would be ln of n plus 4. Yeah. ln of x, I should say. Whatever. Great. I got one more example, and then some for you all. And then we'll talk about a variation on the comparison test. Cosine squared n plus 1 over n. All right? I don't know about you. When I see the trig function in there, the sine or cosine, I'm not into that. I like to see powers of n. That's a p series. And I like to see n inside the exponent. That's a geometric series. But these kinds of trig functions, I don't like that at all. So my impression or my immediate reaction to that is I would like to compare with just 1 over n. Because I don't like this at all. I would like to just throw that away if at all possible. So the comparison will say cosine squared n plus 1 over n. What is it? Less than? Greater than? Yeah? I think it's greater. Yeah, because, I mean, what's the difference here? Here we have 1 over n. This is also 1 over n, but like plus a little bit of extra stuff here. All right? So this is greater than. Now you may be concerned, what if this extra stuff is actually negative? Then it's not actually greater than. But actually that's kind of why I put the squared here. If this was just a straight up cosine, this would be a much more difficult problem to handle. But since it's a cosine squared, it means this part is always positive. So this guy really is greater than that guy. All right? And so we have the thing that I started with is now the bigger, right? And it's greater than 1 over n, which is the smaller. And this one, maybe I'll put my sums here. This one, does that one converge or diverge?
Diverge.
This one diverges. That's the harmonic series which diverges, or you can say it's the p series with p equal 1, the n to the power 1 there. So this diverges. So the smaller one diverges, which means the bigger one diverges. And that's what we had started with. So the smaller, and this is a valid argument, right? The smaller diverges. So that means the bigger one diverges. The end. All right. Make sure you get it the right way around. I find these easy to confuse myself and mess them up. Any thoughts about them? All right, I got some for you all to try. You will have to look at it and decide for yourself what you want to compare it with. Whoa. And as an extra bonus, one of these is not possible to do using the comparison test. So say that for one of them. The other two you can do. See what you think. Chat with your friends about it. In each case, your answer should just be converges or diverges. I would say dancing.
Yeah.
How's it going?
That's good. I would say you can throw away something in there. You have two choices. Just kind of like here. this, so you can do that here.
Okay.
And it's kind of what you
Oh, yeah, okay.
get rid of. This is good. Okay. This is a good idea, but you can use the comparison. Yes, that's true. But these comparisons, I guess, all along, I've been writing straight up here, that's something. It actually works. Okay. This is good. Yeah, which way is that?
Yeah,
That is kind of. That one. Doing okay here? This is good. How's it
No,
going?
those are right.
D. C. Yeah, yes. Can't tell.
Is that because, like, if this is converging, the bigger one could still diverge?
Yeah.
Or is that what
That's true, although there's another reason why you can't use the comparison test on this one. Because, I mean, that just means, well, maybe you shouldn't have done that comparison, maybe there's a better comparison that we
N
could
over
do.
N to the four?
Yeah, I mean, that's something you could also consider. Although, is it really true that N minus N
No,
squared is
that's
greater than one?
yeah, because like it doesn't depend on what N is. Like, you don't know.
Right.
Okay.
Like for, like if N equals 2, that's 2 minus 4, which
Yeah.
is not bigger than 1.
Okay, that's what I thought at first, but then I was like, oh, that's okay.
Yeah. You doing okay?
I just got these two.
Mm-hmm. I said one of them is impossible. You can
Yeah.
comparison test, so
Yeah.
it's that one.
Okay.
All right, can we talk about these? I got one more thing that I wanted to do before we leave today. Oh, I suppose we have time. The one that you cannot do, let's just get this out of the way. I said one of these you can't do with the comparison test. It is this one here. You can't do that with the comparison test. And that's because you have to remember for all of these tests that they only apply in certain situations. And the comparison test, I said at the very beginning, is only for use in series where all the terms are positive. And here, these terms are not all positive. Like, if I use n equals 1, actually that equals 0. 0 is not positive. And if I use something like n equals 2, this up top says 2 minus 4, which is negative. So these terms are actually all negative, except the first one is 0. And then after that, they're all negative. So these, I will say, these are not positive terms. So we can't do the comparison test. All right. If you needed to do this one, you might consider doing the integral test, although the integral test is used for decreasing functions. These are always negative and increasing. There is a version of the integral test which can work for that, but anyway, we are not going to try to do that one. All right. The other two we can do, and as I was going around, I saw most people worked out the first one. The comparison to do for the first one is, I put ln but all by itself. I don't like ln in there just because that looks weird to me. I would rather compare with 1 over n. And that should be a greater because here I just have 1 up top. Here I have 1 plus a little bit more stuff. So the numerator on this one is definitely bigger than the numerator on this one. All right, and 1 over n diverges because that's a harmonic series, or you could say it's a p series with p equals 1. And so what we have here is the smaller one diverges. That means the bigger one also diverges. So the sum 1 plus ln n over n diverges because it's bigger than that other thing which diverges. Right? Most people said something like this for that one. And what about the other one? The other one, in my opinion, is a little trickier. This one here, I can just drag it down. this one here, all right? This one I would like to compare by throwing away one of those terms in the denominator. You got an idea?
Yeah, you do that, and that is greater than the series of 1 over 4 to the power of n. And then you do 1 to the 4 of the power of n with the integral.
Okay. Yeah, I wouldn't do that with the integral test, although you can. This is a little, there's a simpler way to do that. But yeah, this is the proper comparison to use because, well, it's up to you really to decide. In following his suggestion, we throw away the root n and we end up with just 4 to the n on the bottom. Although, it's also true you could have thrown away the 4 to the n and ended up with just the root n on the bottom. I don't know if any of you tried to do it that way. But anyway, doing it this way, did you try to do it that way?
No, how come the inequality is that way?
Because this was big.
It should be the other way. Yeah, I wrote it. Here the denominator is bigger, and here it's smaller. Yeah. Sorry about that. Like so, right? And how do you handle 1 over 4 to the n? I would say that's the same as 1/4 to the n. And this is now a geometric r equals 1/4. You can do that with the integral test, but this is a lot easier. This is a geometric with r equals 1/4, and so it converges. And so here, the bigger one converges, which means the smaller one converges. So bigger converges, so that means the smaller converges. All right, I hope you got something like that. Any questions about that one? I would like to talk about the road less traveled on this one. Like I said before, we decided to throw away root n and end up with this, but you could have also thrown away the 4 to the n. Maybe you don't write this down because actually this is not going to work out. I don't know if anybody tried to do it that other way. What if instead I throw away 4 to the n? Then I could have said this, right? 1 over root n, of course, the same as 1 over n to the half. This is a p series. P equals 1/2, right? I don't know if anybody did it this way. Rather than getting a geometric this way around, you get a p series. Does this converge or diverge?
Diverge.
This diverges, right? P series diverges when, or it converges when p is greater than 1, diverges otherwise. So this one diverges. Didn't we just say it converged in the other way around? What's the, we ought to get consistent answers, yeah. Yeah, right. So actually, nothing that I wrote here is wrong, but this is like a logical dead end. What I've demonstrated is that the bigger one diverges, but that doesn't mean anything about the smaller one, right? If the bigger one goes to infinity, the smaller one still might converge. And in fact, in this example, the smaller one does converge. So this one diverges. So what we've shown is, so bigger diverges. So nothing. That doesn't mean anything, all right? So you're not wrong, it's just congratulations, you played yourself kind of situation. All right? Great. Okay. Excellent. In our remaining 15 minutes, I think we can talk about a slight variation on the comparison test, which in my opinion, when it works, this is actually a little bit easier, in my opinion, than the standard comparison test. And this is referred to as the limit comparison test. If you ask me, sort of like out on these streets, if you show me a series, I'm going to try the limit comparison test before I try the ordinary comparison test, because when it works, I find this to be a little bit easier to manage. You have to be it requires a little bit less creativity. So I will just write it down and then we'll talk about it and we'll do an example or two. So this, again, is only good for positive terms. It's still only used for positive terms, but I will write this like a theorem. It is called the limit comparison test, and it says if, again, it's about comparisons. So if an and bn are positive for all n, And lim n goes to infinity, an over bn is some number, exists, and the c is greater than 0. So if your terms of the two series, when you divide them, their limit is a constant, and that constant is not 0, that constant is automatically going to be positive or 0, because a n and bn are always positive numbers. But it is possible sometimes for this constant to be 0. But anyway, if that constant is greater than 0, then the conclusion is the series an and the series bn have the same convergence. Either they both converge or they both diverge. Both converge or both diverge. All right. What I like about this, I said before, I would prefer to use this rather than the other one. You'll notice here, you can use this to show that things converge without actually thinking about any inequalities. And that's what makes this easier to handle, in my opinion. You don't have to actually think through any inequalities here. You just have to do that limit. And can I just say, maybe I'll say, like, I want to do some examples, but very quickly, why this is true, why you should believe this. This basically means, it means something like, if I were to multiply the b's onto the other side, it means something like an approaches bn times c, or maybe I'll say it this way. An is like close to bn times c for large n, all right? And what that means is basically, this is all slightly informal, but the series of an will be approximately the same as the series of cbn, which is c times the series of bn. And so the two series, they are basically just, the only difference between them is multiplication by this constant. And so that means if one of them converges, the other one also converges. And if one of them diverges, the other one also diverges. Like if this one is infinity and the constant is, say, 2, then this one is like 2 times infinity, which is still infinity. That's the idea here. And this is also why it's important that c is greater than 0. If the c really is 0, then actually it is possible for this to diverge, but this one still like equals 0 or something like that. But we don't consider the case when c equals 0. So this is basically why it's true. So the series an and the series bn have the same convergence because they're basically just like different by a constant multiple. All right, anyway, let's just try an example. I got 2 examples. I think that'll be enough. So let's try the sum 4 plus n over n to the 4. All right. Now, it is still up to you to cook up the other series out of nowhere. So you are going to still think about, I'm trying to compare this with some other series. And you have to just come up with the other one all by yourself. This one here, the basic strategy is this one, when we consider the most significant terms. By that I mean something like the biggest powers on the top and on the bottom. And this is there's a little finesse to this. You have to get a feel for how you're generally going to approach these. But in this one, when I consider the most significant terms, it's basically n over n to the 4. Like that 4 plus doesn't make much of a difference up top, right? That's my feeling about this. Because, of course, in the series, like when you go down enough terms, the n is going to be super big anyway. So the adding 4 in the numerator really doesn't make a difference. All right. So this is basically n over n to the 4, which, of course, can simplify to 1 over n cubed. And so that's the comparison that I'm going to do. So we're going to compare with this other series, 1 over n cubed. All right. Now, if you were using the ordinary comparisons, you would have to make some inequality here. But for the limit comparison, it's easier than that. So I'm going to do the limit comparison. Remember what it said? It said this thing. Lim n goes to infinity, a to the n, an over bn equals c. So I go lim n goes to infinity, an over bn. All right? Where an is my original series, so that's, or my original terms, just as a sequence, 4 plus n over n to the 4, divided by bn is the one that I came up with, 1 over n cubed. And what I want is to show that this limit equals a constant which is not 0. Hopefully this limit is equal to a constant that's not 0. What is it? You've got to do some simplifying here. That, I guess, is the same as putting a n cubed up top, right? So this is the same as 4 plus n times n cubed. Right? In it? As the Brits would say. Distribute up top, and it's 4n cubed plus n to the 4 over n to the 4, right? And now this is an ordinary limit of the type that we've done many times before. You would divide through everything by the highest power of n here, which would be n to the 4. That's going to be 4 over n plus 1 over 1, right? If I actually divide through by n to the 4. And what's the lim of that going to be? What do you think?
1.
I think it's 1, yeah. 4 over n goes to 0 when n goes to infinity. And then we just are left with 1. All right. Is that a constant greater than 0? Yes, it is. So, well, I'll say this is greater than 0. Right? The 1 that I got there is greater than 0. So the conclusion is our two series have the same convergence. They were 4 plus n over n squared, and the other was 1 over n cubed. Have the same convergence. And what is it? Do they either they both converge or they both, sorry, did I write this wrong? N squared, it ought to be n to the 4. Over here, I wrote that wrong. N to the 4, like so. All right. Either they both converge or they both diverge. What is it? Yeah.
They're like converge.
Yeah. Why? How do you know that?
Took the series 1 over n cubed and found it to be p series with p equaling 3.
Yeah. Right. This is a p series. P equals 3. And so it converges. And that means the other one converges. That's how we do it. All right? Any thoughts about that? This is the limit comparison test. It is still kind of involved, and you still have to invent this out of nowhere. Not really out of nowhere, but you have to know how to kind of look at this and turn it into this thing that you compare it with. All right? I got one more, and then that'll do it for us. Let's try that one which I sort of left you hanging on before. This one you could actually do with the integral test, but I want to do this instead using the limit comparison test. This one actually does diverge, but let's try and do this with the limit comparison test. Again, when I look at this, I view that plus 4 as more or less insignificant. So this looks like just 1 over n. That's what I'm going to compare it with. All right, so I'm going to do the lim of my original sequence, 1 over n plus 4, divided by my new sequence, which I'm comparing to, which is 1 over n. And then, you know, simplify whatever here. I guess we just flip over the thing on the bottom. Keep flip. There's some slogan that people say about this.
Keep change flip.
Keep, change, flip. Yeah, I don't know what that means. I hear people say it sometimes. I don't say that. I have my own silly slogans, like Shun. All right, anyway, what's the limit of that? We do the thing, you divide out by the ends. This is a fairly straightforward lim to do now. It's 1 over 1 plus 4 over n. And then take the limit, that 4 over n becomes a 0. You get 1, all right? 1 is a constant. That's what we're looking for when I do the limit thing here. This is a constant which is greater than 0, all right? If you get 0 there, it means you chose the wrong function to compare it with. Or maybe it just means you can't do the limit comparison test for this example. But anyway, that means the series 1 over n plus 4 and the series 1 over n have the same convergence. And what is it? Converges or diverges? It is diverges, because 1 over n is the harmonic which diverges. This one diverges. That's the harmonic. So the sum 1 over n plus 4 diverges. All right, that'll do.